Swayam Prabha. Digital India. Educated India.
Welcome to Module C, Lecture 4. In this lecture, we shall discuss about queuing analysis. In Lecture 3, we took up two example problems to explain you the quantitative analysis of shock waves, then also discussed about shock wave propagation, three scenarios, small discontinuity in traffic densities, then complete stopping situations, and then starting situations. Then we took an example problem to show you sample calculations, how we can calculate various parameters under these three scenarios. With this background, today we switch over to the next topic, which is queuing analysis. One of the greatest concern to traffic engineer is the high congestion level on roads and highways. Especially we find such high level of congestion during the peak hours or the peak period. And the loss is enormous due to congestion and queuing. The congestion results in the formation of queues on several facilities such as on ramp, off ramp, in the context of expressway or controlled access facilities, at signalized and unsignalized intersections, arterials, etc. And we know that traffic queue and congestion in peak period cause significant delay, loss of performance and overall economic loss due to congestion, and queuing is also enormous. So, an understanding of the process that leads to the occurrence of queues and subsequent delays, loss, all other things is essential for the proper analysis of the effect of queuing. So, that is our interest, why we discuss this topic, queuing and analysis of queuing. When we are talking about the analysis of queuing or even the demand supply part, the imbalance, the congestion, the queuing, then three aspects are very, very important. One is what is the traffic demand, what is the observed traffic volume, and then what is the capacity of the facility. So, one end the capacity, another end observed traffic volume, and then what is the real traffic demand. So, let us quickly understand these terminologies more clearly before we proceed further. First, traffic demand. Traffic demand normally or in a simple way can be defined as the number of vehicle desires to pass a point of the road in an hour. The key word here is desires to pass. The number of vehicle desires to pass a point in the road in an hour, and we express it in terms of vehicle per hour or person per hour. What is the observed traffic volume? The actual number of vehicles that is passing a point of the road again in an hour and can be expressed in terms of vehicle per hour or even sometimes the observed volume may be also in passengers per hour, overall passenger. I mean, when we say traffic volume, obviously the measurements has to be in terms of traffic only, but similar expression is possible even in terms of number of persons per hour, we can express that also. So, here the key word is actually, or the portion that is actually passes a point. Desires to pass a point is the demand, actually passes a point is the real observed volumes, what we are observing in the field. Traffic capacity on the other hand is the maximum volume that a particular segment or point on a facility can accommodate. What is the maximum volume? So, here that is the maximum volume, that is very important, the maximum volume that a facility can accommodate. Again, normally when we say traffic or vehicle, then obviously vehicle per hour, but capacity can also be expressed in terms of number of persons per hour. So, there are three aspects, as I said. One way, number of vehicles desires to pass, that is the demand, actually passing, that is the observed traffic volume, and what can be the maximum number, that is the capacity. Physical system, road is a physical system. So, any physical system will have a capacity. So, a road also has a capacity. Now, when the traffic demand is less than the capacity, that means the actual demand is less than the capacity of the road or capacity of the system. In that case, observed volume is equal to the traffic demand. Then these two measurements, traffic demand and observed volume, will be same, because there is no capacity constraint. So, the whole demand, the complete demand can pass through the road. So, whatever we will measure on the field, whatever we will measure in the field is actually the demand. But when traffic demand is greater than the capacity, in that case the observed volume is not the actual demand, because observed volume will be in that case is less than the actual demand, because the demand is actually greater than capacity, and what theoretically maximum can pass through that section is the capacity flow. When such kind of situation we face, like the demand is greater than the capacity, then usually congestion is present, because traffic state will be very different. We have already discussed this in module B and also partly in module A, partly in module C itself, previous lectures. So, you know it. So, in that case, once the congestion is happening, also there will be queuing, then drivers choose to travel to alternative route. They may not like to travel on this route, because there is no capacity left. So, they may be forced to travel to some other route, or may choose to travel at some other time, or sometimes even change the destination, except for necessary trip. If it is work trip or education trips, you cannot change the destination. But if it is a shopping trips, one may choose to go to another shopping destination, if the situation is so, right, or even in worst case may cancel the trip also. That could be also an extreme situation, that wanted to visit a recreational or social trip and that got cancelled as well, right, because of the congestion and because of the bad traffic situation. So, on congested corridor, if we measure the volume, and whatever we will be able to measure may not be the actual traffic demand. Actual traffic demand is something very different, and measurements only on that congested corridor, where the demand is actually more than the capacity, will not give us the true demand or the actual demand. It is something like very similar, that if we have a bucket and the capacity is 10 liter and I want to pour 15 liter of water in that bucket, the bucket can only retain 10 liter and the 5 liter will spill over on the ground, right. But it is similar thing, that a system has got a capacity, a road also has got a capacity, like a bucket has got capacity, a road also has got capacity. So, anything more you try to pass through right, as we are trying to pour 15 liter water in a 10 liter bucket, right. So, similarly, the demand is actually, if it is more, only the portion what road can take will get accommodated in the road, right, and the remaining somewhere or other will be there, maybe on some other route, some other time, some other destination, even cancelled also, right, all such kind of things will be there. So, the actual demand on a congested corridor can only be obtained by adding up several components, where the demand is more than the capacity. First, obviously, a component which is very important and common is the actual volume passing to the study location or study section, because up to capacity in general can be accommodated. So, that is what we can measure. Then what are the volumes in alternative route that would pass the study section or location in the absence of congestion. So, that is no more here, but it is on alternative routes. Similarly, volume passing the study location at a time other than specified time, which would have occurred in the absence of congestion. That means, if the demand is actually more than the capacity at 10 o'clock in the morning, then instead of travelling at 10 o'clock, maybe some people will travel at 12 o'clock. So, it will be there at 12 o'clock, not at 10 o'clock. Then volume travelling to alternative destination, as I said, where alternative destination is applicable, may not be applicable for shopping work trip, because office location is fixed, you cannot change. School location is fixed, you cannot change. So, educational trips also may not change, right, but shopping trips easily can change. Even the recreational trips, destination, alternative destination may be possible. So, volume travelling to alternative destination, not all volumes, but that volume which could have travelled through the same route in the absence of congestion. Finally, the last bit, trips that does not or that do not occur due to congestion. Trips that do not occur due to congestion, altogether cancelled. So, if we add up all these components 1, 2, 3, 4, 5, all components if we add, we can then get the actual demand, not only by measuring traffic volume on the study location, that is only one component. Among all these, only the observed volume is easy to measure in the field. What we are observing, it is very easy to measure that. Even all other components can also be measured somewhere or other through various or well designed field studies, except probably the last one, that the trips which do not occur due to congestion. Now, coming to the relationship between demand, volume and capacity. Let us consider that the travel demand on a given road, actual true demand on a given road is like this: 50 vehicle per minute for the first 30 minutes, 0 to 30 minutes, then 120 vehicle per minute for the next 30 to 60 minute, that duration, and then comes down to 65 vehicle per minute afterwards, that means beyond 90 minutes. Whereas, the capacity of that section is maybe 75 vehicle per minute, and capacity relates to the physical environment, the physical road, how much width is available and shoulder is available, and all such things will decide what will be the capacity. So, capacity may not change for a given road over time. Now, clearly you can see here the demand exceeds capacity in the time interval of 30 to 90 minutes, where the demand is actually 120 vehicle and the capacity on the other hand is 75 vehicle per minute. So, obviously, during this period demand exceeds the capacity. So, if you look at the demand first 30 minute, this is 50 vehicle, then 30 to 90 minutes 120 vehicle, then comes down to 65 vehicle, all are shown using the green lines, and the capacity is constant at 75 vehicle per minute. So, this is the period clearly where the demand is more than the capacity. Now, what is the queue length during the period when demand exceeds capacity? It is basically the area between the demand and the capacity curve. So, that many vehicles, that is basically the excess demand. So, how we can calculate? We can calculate it easily, that this is 120, this is 75. So, 120 minus 75, and for how much duration? 90 minus 30. So, for 60 minutes. So, we know that excess overall, what is the queue length, how many vehicles will be in the queue because of the shortfall during this 1 hour duration 30 minute to 90 minute is 2700 vehicle. Now, how long it takes to dissipate the queue after 90 minutes? Because after 90 minutes the demand is actually lower than the capacity. So, in general we can assume that the road can discharge at capacity rate, at the rate equivalent to capacity, and therefore, the queue slowly will come down. But how long it will take? This accumulated queue divided by rate of dissipation. What is the rate of dissipation? 75 is the capacity, 65 is the demand. So, you have 10 excess vehicle can be accommodated every minute from the skewed vehicle. So, there are 2700 vehicles. So, 10 vehicles every minute. So, it will take 270 minutes to clear this queue. So, beyond 90 minutes, what has happened between 30 to 90 minutes, it will take 270 minutes to clear that queue or clear that impact. Now, at this location, what is the observed volume with respect to time? So, demand is something we know clearly, what will happen we know, but then with that what is going to be the observed volume? 0 to 30 minutes the observed volume will be 1500 vehicles. So, 50 into 30 minutes. So, 1500 vehicle. 30 to 90 minutes actually we will observe 75 into 90 minus 30 60. So, 4500 vehicle, and 90 to 360 minute we say 270 minute it will take, right, to clear that backlog or the queue. So, 90 to 360 minute observed volume will be equal to the capacity, as queued vehicles do not completely dissipate before this 270 plus up to this time clock is 90 minute. So, 270 plus 9 minutes. So, up to 360 minute. So, next 270 minute or altogether time clock wise it will go up to 360 minute, right, to clear this backlog vehicles, right. So, up to that we will also observe that the observed volume will be equal to capacity. So, the observed volume will be equal to capacity from 30 minute to 360 minute. So, now you can compare easily what is the actual demand and what we measured, right. So, what we measured is not really the actual demand during each of the period. In the first 30 minutes it is whatever we observed and whatever we measured, these two are equal, but beyond that 30 minute up to additional 270 additional 270 plus this 1 hour 30 to 90, right. The demand what you will see observed volume will be equal to capacity, but that is not the true hourly demand. It is happening because of this bottleneck situation, demand supply imbalance, and clearing that effect is taking a long time. Obviously, beyond 360 minute time clock wise, observed volume again equals to the demand. Now, this formation of queues and how or what will be their impacts. Queues will form when the breakdown condition occurs, that means arrival rate exceeds the capacity, and this kind of situation is common on ramps, off ramps, major march point. Off ramps it may not be there, but more on the on ramps when entering, such kind of things are more common. Major march points and at intersection location. Let us take an example of major march point. Let us consider this two approach 1 and approach 2 are meeting, and then this section the traffic demand is getting served. So, on approach 1 and approach 2, the capacity is more than demand flow rate, because here you can see the capacity C is 4000 vehicle per hour, demand is actually 3800 vehicle per hour, which is less than the capacity, and therefore, the actual observed volume also will be 3800, but that observed volume will be somewhere upstream, not right at this junction, right, not at this very near or close to this merging point, but somewhere further upstream, right. The reason I will explain. But in general, we can say if we are taking some distance away from this junction, we can get that observed volume also as 3800, which is actually equal to the demand. So, generally no queue should form if you only consider this demand and this capacity. Same thing is here in approach 2, your capacity is 4000 vehicle per hour, but the demand is 3600. So, further upstream somewhere away from this junction, if we measure, we should get the demand and observed volume same. But what is happening when from both these approaches traffic is trying to enter to this section? So, then the total demand will be 3800 plus 3600, which is 7400 vehicle, but what is the capacity here is 6000. So, all those vehicles cannot really enter in this section. So, there will be congestion, there will be queue, and that queue effect will be there on both approach 1 and approach 2. So, you will not get observed volume as 3800 or on approach to 3600 if you measure it immediately, but beyond certain points away from that junction you will get this volume. Now, queue will start at march point and then propagate upstream. What will be the rate? Rate will be 7400 is the demand, actual capacity is 6000. So, shortfall is 1400 vehicle per hour. At this rate the queue will start building. Observed volume on the downstream will be equal to 6000 vehicle. If somewhere here, if we measure the volume, we will get 6000, because 6000 volume is able to pass through. Measurement for observed volumes should not be taken within the queue, because then you will not get here 3800 or on this approach 3600, it has to be away, right. Now, observed volume at the downstream may not be exactly equal to the capacity, because we know, I have mentioned this, that the queue discharge rate is generally slightly lower than the capacity. Whenever the queue formation will happen, the discharge may not happen exactly at the rate of capacity, but it will be slightly lesser than the capacity. Now, let us explain you the concept of bottlenecks, hidden bottlenecks and demand starvation. A section of the highway having 2 on ramps and 2 off ramps, you can see there, these are the 2 on ramps, these are the 2 off ramps, and these are the section S1, S2, S3 and S4. Now, the observed volume on S1 and S2 are 2200 vehicle and 800 NT through 2 also will be 3000 vehicle per hour, and observed volume on S 3 will be different, because here you can see the actual demand on S 3 will be 3700, because 2200 plus 800, 3000 plus 700, 3700, that is the observed demand, but the capacity is 3400. So, what you will observe is actually only 3400 the capacity flow, not beyond that, right. Similarly, on S 4 the actual demand is 3700 minus 500. So, 3200, but what is the capacity is 3000. So, you will actually observe only lesser than that, because the exit ramp will take in proportion. So, you will have 3400 total minus, then how much will go here? If it would have been 3700 the total one, then 500 would have exited in proportion, then 500 by 3700 into 3400. So, this much less vehicle will be there, and this many vehicles will actually take this exit ramp. So, there will be 2941 vehicles. So, what we are assuming here, that distribution of observed vehicle is assumed to be same as distribution of demand. So, if there are 3700 vehicles on S 3, if then 500 will go there. So, as it is not 3700, it is 3400. So, in proportion the vehicle will exit. Similarly, observed volume in S 5 will be how much? Here you have seen that S 5 would have been actually demand wise very different, but again due to the same reason, the bottleneck situation, it will be 2941 minus the 3200 is the actual demand. So, if it would have been 3200, then 400 could have exited. So, now it will be 400 by 3200 into 2941. So, 2941 minus this quantity. So, 2574. So, these whole analysis then will reveal that section 3 is the bottleneck. If you look at this analysis till this time, you will only feel that bottleneck is there only in section 3, because in all other cases the actual volume, what will be observed, the actual volume I have given here, observed volume on S 1, S 2, S 3, S 4 and also in S 5. So, the observed volumes will be lesser than capacity except for S 3. So, if we go by measured volume, we will feel like the major problem is only in S 3. Because S 3, this section is the bottleneck. So, the general tendency will be what? Let us increase the capacity of the bottleneck. So, because that is the problematic section. So, you increase it. Now, suppose we increase the capacity of section T to 4000 vehicle per hour, then this section is no more the bottleneck. So, now the whole demand 3700 will be able to pass through this section. So, with that what will be then S 3? S 3 is 3700. What will be then S 4? S 4 will be 3000 vehicle. Why? Because demand is actually 3200, because out of 3700 500 will exit and 3200 will be there, but then this capacity is 3000. So, only 3000 vehicle will be able to pass through, not the whole demand. So, now S 4 will be our new bottleneck. Earlier we could not identify S 4 as a bottleneck. Earlier analysis, because S 4, S 3 was bottleneck, the way the demand was happening, if by measured volume and the capacity if we compare, we only found that S 3 was a problematic location. But now you have removed the bottleneck at S 3. So, now you realize actually the bottleneck is S 4 again. So, removing S 3 bottleneck does not help completely. You also have to consider that S 4 is another bottleneck. But this potential bottleneck in section 4 was hidden by the fact that section 3 did not allow the true demand to proceed to segment 4. Because of the bottleneck, earlier case the demand which was passing through section 4, passing to section 4 S 4 was constrained. So, we did not realize that actually there is a capacity constant. So, this is called hidden bottleneck. So, S4 actually was a hidden bottleneck, which could not be identified based on this analysis. We could only identify S4 when we remove the bottleneck at S3. So, S4 may be considered as hidden bottleneck. So, altogether as I said, improving section 3 without improving section 4 does not resolve the problem completely, it removes the problem partially, because now S3 bottleneck is removed, and rather what happens, the bottleneck point is shifting. Earlier S3 was bottleneck and now S4 is bottleneck. So, the careful analysis needs to be performed to identify bottleneck locations, so that improvement can be done at all such locations. And eventually what happened, bottleneck at section 3 starves the demand to downstream point section 4, because of its low capacity. The throughput from that section was constrained. So, it was actually creating hidden bottleneck 4, and because the whole demand was not reaching to section 4, we can call it as demand starvation. So, not the actual whole demand is able to reach even to that section. So, what is reaching is not actually the true demand. The true demand is something lesser than that is reaching. So, demand starvation is happening. Design and control must take into account the potential existence of this hidden bottleneck. Now, let us quickly try to understand capacity versus Q discharge. Now, as you know, the capacity is the maximum flow rate obtained in an hour under stable flow condition, and usually occurs for a short time before a breakdown occurs. And after the breakdown, vehicles are actually discharged at the Q discharge rate, not that capacity, and the Q discharge rate is slightly lesser, maybe 5 to 10% lesser than the capacity. Okay. It is important to understand that the Q discharge rate and its influence on the breakdown and queuing. So, let us take an example problem to explain you that more clearly. Consider a scenario where one truck is stalled at one lane in a 3-lane highway. There are 3 lanes 1, 2, 3, and one lane is blocked because of a stalled truck. A truck sudden breakdown probably happened, and therefore, it is occupying that lane, and that happened between 6 and 6:30. That means, by 6:30 the vehicle is cleared only for half an hour. Now, what are the demand flow rates? Demands are between 6 to 9 am 6,000 vehicle, then come down to 5,000 during 9 to 10 am, and then further come down to 4,000 vehicle during 10 to 11 am. If that is the demand, let us assume that the capacity and Q discharge rate is equal initially, equivalent to 2000 vehicle per hour per lane, standard capacity. Then what we want to find out here, what will be the size of the Q during different hours, and by what time the Q will be completely dissipated. Let us go through this simple calculation. Time 6 to 6:30, the rate of arrival is 6,000 vehicle per hour, but so in half an hour how many vehicles will be there? 3,000 vehicles, because this is per hour, and so in half an hour 3,000 vehicle. Departure rate is 2,000 vehicle per hour, but in half an hour actually how many? 2,000 vehicle into 30 minute 0.5 hour into effective there are 2 lanes out of 3 lanes. So, total 2,000 vehicle can be discharged. So, arrival is 3,000, discharge is 2,000. So, what will be the size of the queue? Is the remaining vehicle. So, 3,000 minus 2,000 is the 1,000. Now, 6:30 to 7 o'clock again 6,000 vehicle, again 3,000, again departure rate 2,000, but now the breakdown vehicle that has been removed. So, you have all 3 lanes available. So, 30 minute 2,000 per hour per lane. So, 1,000 vehicle in half an hour per lane multiplied by 3 lane. So, we are able to discharge 3,000 vehicle. So, what will be the size of the queue? Size of the queue will be this 1000 vehicles which were there already from the at 6:30 plus here 3000 vehicle arrival and 3000 vehicle discharge. So, 3000 minus 3000. So, it still remains 1000. 7 to 8 again 6000 vehicle in the hour, arrival during this whole hour is again 6000 here, because we have taken 1 hour duration here. Earlier cases it was half an hour, but 1 hour, departure rate same. So, here also 6000 vehicle will get discharged. So, whatever new vehicles are entering, that many vehicles are able to get discharged. So, the queue remains, the queue 1000 vehicles in the queue will still be retained. Now, 8 to 9 o'clock is still same 6000, 6000, 2000, 6000 and 1000 vehicle, but then from 9 o'clock, as it has been told that 9 to 10 the vehicle is 5000 vehicle per hour. So, 9 to 10 o'clock the demand is 5000, but so a vehicle arrival is 5000 and here it is 2000. So, the departure could be 6000 as per capacity. So, 5000 here, 6000 here. So, these 1000 vehicles which were there in the queue are getting discharged. So, what you are getting actually 6 to 6:30 the truck was occupying one lane and that lane capacity could not be utilized. Because of that, whatever queue will be formed, that impact will be there up to 10 o'clock. Even though after 6:30 that vehicle is removed, 3.5 hours still that impact will be there. So, anybody entering will still find there is a queue, although that truck is no more existing. So, maximum queue length here is 1000 vehicle, you have seen here. Any vehicle comes to the site between 6:30 to 9 am, the vehicle truck will not be there, but the queue will be there, and average queue length per lane will be 333 vehicles, because 1000 vehicles. So, 3 lane, if we assume they will get evenly distributed. So, they will join a queue of any lane, they will join a queue of 333 vehicles. Even if obstruction is cleared at 6:30 am, queue is completely cleared only at 10 am, and in this case the queue discharge rate and capacity we have assumed same, but in reality the queue discharge rate will be lesser. If we assume that queue discharge is not 2000, but it is 1800, right, 90% of that 10% drop. Then how it will happen? A very similar calculation is shown here, and here interestingly we will see that because the capacity or the discharge is lesser, the queue length will go even longer. What you got here as 1000 vehicles maximum, not in the queue, it is in different lane, but total accumulated vehicle in the queue is 1000, but here it is going up to 2700 and it is taking up to 11:39 am to actually clear this vehicle, because we simply the way we were calculating, we calculated here between 11 to 12 o'clock, but then the number becomes negative, that it indicating that it does not require time up to 12 o'clock. So, we calculated it that it is 4000 is the arrival and 5400. So, 1400 vehicles, additional vehicles can be cleared in 60 minutes, and we have only or 1 hour, and we have only 900 vehicles. So, how much additional time it will take beyond 11 o'clock is can be calculated very easily, and that is 11:39 am. So, what we observe altogether, that maximum queue length is 2700 instead of 1000 vehicle. So, the moment the actual queue discharge rate will be like this, lesser than the capacity. So, how it impacts the queue length? Any vehicle comes at the site at AM, joins a queue of 700 vehicles. Take any lane, you have to be at the back of 700 vehicle, whether it was 3:30 vehicle in earlier case. If an obstruction is cleared, even if the obstruction is cleared at 6:30 am, the queue is completely cleared at 11:39. It takes much longer time. Earlier we could clear it only by 10 o'clock, right, and now we are able to clear it only at 11:39. So, by comparing these two scenarios, it is also shown that how the queue discharge rate significantly affect the queuing process, and the overall queuing process is explained through this example. So, altogether we discussed here about the concept of traffic demand, volume and capacity, what is the relationship between demand, volume and capacity, how the queues are formed because of this imbalance between the demand and the capacity, and how the bottlenecks, the concept of bottleneck, hidden bottlenecks and the demand starvation, and also took an example to explain you the capacity versus queue discharge, how it changes. With this, I close this lecture. Thank you so much.